Hello, Maurits here. Today we will look at the orbital period of the Moon. And to do that we make this little model here, right? This is the Earth, this is the Moon. They have some distance from each other, and we googled for the average distance to the Moon. We would find 400 kilometers, or 3.844 times 10 to the power of 3, 4, 5, 6, 7, 8 meters, right? And the Moon is going around in an orbit with that radius, and of course it's pulled down by the force of gravity, and the force of gravity acts on the Earth in that opposite direction. And that will also be an acceleration. We found previously that acceleration due to gravity is g, in this case mass of the Earth over r square. But we also know that this force inward here will be the centripetal force that keeps it in orbit. And we had a formula for the centripetal acceleration, and that was v square over r, and we can put them to be equal since this one is caused by that. So we get g m over r square equals to v square over r. We can cancel away 1r against the other 2r, so we no longer have rr, we have r. We can now make v our subject, so we have g m over r, and then we can take the square root of that to get the velocity. But it was not the velocity we were after. We were after the orbital period. Okay, so we know when something goes in orbit, the velocity is the distance over time, right? Or anything. Velocity is the distance over time, and when it's in orbit, the distance would be 2 pi r over the period. So I can make the period my subject here and say that would be 2 pi r, divide down the v multiplied up to t, so that will be this, right? And on that formula we can now fill in this, so 2 pi r over square root of g capital M over r, write this like this. I write this as 2 pi, and I will write r as a square root of r square, just to be able to combine it with other square root. And this will give us 2 pi square root of r square over g m over r. I will multiply both the numerator and denominator here by r, cancel cancel, and that will give us that the period is 2 pi square root of r cubed over g m. So we now fill in the numbers. 2 pi first. 2 pi square root of the radius cubed, so that would be 3.844 times 10 to the power of 8 to the power of 3 over g, that we have value 6.67 times 10 to the power of negative 11 on, times the mass of the Earth that we found in a previous video was 5.97 times 10 to the power of 24. And now we take our calculator and calculate this. So I will take 3.844 x 8 to the power of 3 to start with, divided by bracket 6.67 x minus 11 times 5.97 x 24 in bracket. Then we take the square root of this and multiply by 2 and multiply by pi to get the amazing time of 2.373 seconds, about 2.37 million seconds. And that is not a unit that is very useful in everyday use. So we take this number, we divide it by 60 to get the minutes, we divide by 60 to get hours, we divide by 24 to get days, and we find this to be 27.46 days, 24-hour days. Oh, and that is quite reasonable, right? If we Google for the orbital period of the Sun, we will find a value of 27.3 days. We're off a little bit. Reason for that is that we used average distance and so on. There are several things that is only simplification, but close enough. But if you Google for the length of, so that's, by the way, first we realize what we've done. We have been able to use this formula to figure out the orbital period of the Sun. We use the same formula to figure out the mass of the Earth, and we use that mass in here. So that means that the force that we have of gravity acting on you down on Earth is the same force as what keeps the Moon in orbit, and that was the Newton's big insight. He realized that these must be the same force. Anyhow, if you Google for length of a month, you will find that it is 29.5 days. So this is very much off, right? No, not right. The reason for this discrepancy is how we calculate the days. If the Sun is here and the Earth is here and it rotates about, we calculate a day from when, say, midday, and then it rotates about, and at the same time it moves over here, we get a new midday. They won't point in the same direction in space. So a day is not really correct from an astronomical standpoint. And this time we have here is the time for it to orbit according to ordinary days, which is not the same as the days we need there. So those two numbers will be different. If you do the careful calculation on that too, we will find this number in the end. But it's pretty cool that we've been able to do these two calculations. I had a student a few years ago who did this little thing. He calculated the distance to the Moon by taking 3 people on Earth and measuring the angles to the Moon. And I think it was in China, Sweden and India or something like that. And using these Y3 points then we can figure out what we need to make this go into 1 point. So he found a value that was within plus minus 30% or something like that. Interesting enough, for those of you out there that think the Earth is flat, if you try to draw these 3 lines from a flat Earth, they will not converge to a point. Go figure. So that is rather interesting by itself. But we use the distance to the Moon. I can mention the Maya Indians knew the distance to the Moon with higher accuracy than we knew in Europe. That is pretty cool. They use basically the trigonometric methods that we use today. But anyhow, I think this is pretty cool. So, ciao.